Okay, so we have right now, this is going to be a lecture about the introduction to finite elements, and the very first lecture I'm going to talk to you about what finite elements are, and we're going to use this beam, which is a simple supported beam with moments, with a moment applied to it in such a way that we will understand the very basic fundamental idea behind finite elements. So that's the objective of this, is to use some methods that will obtain a solution for this beam. Obviously, one of the questions and that comes up immediately after we said something like this is, what is the deflection of the beam? That's our objective here. All right. So to that end, we have applied this moment in here, you can see here, and that causes the deflection of this beam. So how do we represent and calculate this deflection is the question. So you find the solution for this deflection. Now, we know that there is a differential equation that controls the deflection of this beam. We know from our strength of materials courses that EI and d square y dx square minus the moment equation is going to be equal to 0. So this is the equilibrium of this beam. We don't have a time-dependent term over here because this is a static problem. In other words, simply said, regardless of time, you have this beam with the stiffness is I and this applied moment m0. Question, what's the deflection at every point between our origin, which we could say is 0 over here, and then h over here? Yeah? So what is the deflection? To this end, you see you have we have graph on this bottom picture here the moment of this beam. But obviously the moment of this beam is going to be just a straight line because it's just a constant moment. If we had a load on the middle here, then we wouldn't have this constant moment. We would have a moment that varies from 0 to a maximum value in the middle, then it decreases from the maximum value in the middle to the other side. Okay? So I just want to make sure everybody is on the same page as to what the problem is. Problem here is to calculate the deflection of this beam given this load. All right? Now, we have several methods of doing this. One of them is the exact method, and another one is going to be an approximate solution that would lead us into the idea of doing finite element model. So if we go down here to the next slide, we can say that we can safely say that the deflection of this beam, this line over here, actually resembles a sine function. In other words, you see, we can say, okay, let's write down here. See, what is the nice part about having all this fencing here? I'm just gonna write it down for a moment in here. See, here's the beam. Perhaps we should do it more professionally here. How about there? There we go. I like it. Then we have this over here, and maybe I think that's the way it was. Yeah. And then we'll erase this one. Isn't this cool how we can do this? Yeah? Okay. What I'm trying to say is that if we were to set a coordinate system over here with y, a coordinate system over here with x, isn't it true that the deflection, as we see here, the deflection of this beam that is subject to this moment and subject to the moment over here, like this, will have values at every value of x, you see, between 0 and h being the length. Yeah. This function, as I said, resembles a sine function, and you may say, Professor, how is that? Let's just do this right, because I think need to begin doing things correctly here. And there we go. Let's say this is the line that I'm trying to say. Yeah. Look, I go in here and I say, okay, this is the function like this. See? Where are we? No, yeah. Isn't you see, this function, an approximation of this to a sine function. I mean, I didn't think it was enough to just say it, but I wanted you to see it, that this would be a sine function that would be forever and ever here. It just happens that we are going to steal just a little piece of that, and we're going to call it that's the deflection. But you see, if we go back to the slide over here, we say, okay, we have two possibilities. We make an approximation like this, see, where y of x is equal sine of pi x over h, where x is the variable, yeah? Or we say, okay, we are going to produce the exact solution. How do we do this? You may recall from the solution of differential equations, in this case second order partial differential equations. This is a very simple second order partial differential equation. It says d squared y dx squared equals to mx over ei. That came from this equation over here. See? Yeah. We say, okay, this is the challenge now. We have to produce an exact solution of this equation. If you integrate once down here, what will happen? If you integrate once, you're going to get dy dx, this one right here. So you say mx ei, you integrate once, both sides here, you integrate both sides, and then of course dy dx becomes mx EI plus C. And then if you integrate another time, you're going to get m is equal to mx squared over 2ei plus c1x plus c2. So this is one of the methods that you might have seen in your strength of materials class. There are several methods, double integration method is what we're doing here. There's others like Castigliano's theorem, and that leads to the same answer. The point I'm trying to make is that this beam that you see over here, this one, has an exact solution. And that's what we're trying to find. So this one here would be the solution. Y as a function of x at any x will produce the value of y. Now, one of the things that I need to say is that all these finite element problems, they are called boundary value problems. It means that we have the initial value on one side, and we also need another boundary value. See, the problems that are dynamic, they are called initial value problems because they start at a certain time, and then you ask the question, what happens with the system after a certain time? Here, the situation is not like that. They're called boundary value problems because we know what the value is at the origin and at some other point. We need two values. In all finite element problems, you always get some initial values like this. Like in this case, you see on the right hand side, we can very easily point out in here that the boundary condition says that y0 is 0 at the origin, but there's also 0 on the other side. See, that's what we're saying here, is that for the beam, you see in here, that condition says that, well, it's very obvious. See, on this side, y of x equal to 0 is 0. But if this length is h, we are also saying that y of h is equal to 0. You see what I mean? These two are very important because the deflection, which is the question here in this case, is being asked, what's the value of this deflection in between these 2 points? And so this way we narrow our problem a lot. We narrow the problem, and we narrow it to the point that we can say, okay, we have initial value, we have boundary value problem where the deflection y is 0 at the origin, and y is also 0 at the value of h. Okay, because of that, because of what I just said, then it follows that we can continue with the solution. See here, if you say that y is 0 when x is 0, C2, this one is 0, right? If you plug in the values of the two initial conditions on that equation on the left on the bottom, it's very obvious that you will find the value of C2. the value of C2 is 0. But you see, if you put the other initial condition on the next line and you say the value of y is 0 when x is equal to h, so you get this equation, you see? You get this equation right here. There, this one. Yeah? And if you do that, then you're gonna find the value of C1. Well, everything sort of falls into place after that, because if you have found the value of C2 and C1 and you replace them on this equation here, for sure you know this is the final equation. All I have done here is just factor this a little bit and conclude what is the exact solution. Okay, so I think that's what we have found out right now. But what will happen is that we need to establish a principle that not all problems would follow this solution, that it was as easy as this one. And for that reason, we need to find out a way to approximate this. So in your book, on chapter 1, you have a description about how to find an approximate solution to this. The approximate solution is described on page 4. Yeah. See, the title that he uses is a solution of boundary value problems. And then it says that you have an exact solution, but then you have also an approximate solution. Of course, people have been thinking about how to do approximate solutions for years, and some have come up with different ideas, different methods. In fact, the author of your book lists on page 4 and 5, page 4 and 5, he lists a method called finite difference method, a variational method, the weighted residual method, there's the collocation method, subdomain method, and the Galerkin's method. Okay, so in this particular case, we need to use this example as an example on how to obtain this approximate solution. I think what I'm going to, in order to reach that objective, what I am thinking to do is to use the examples that he has in here, simple example, and illustrate how you actually find this approximate solution. Okay? There are several ways of doing that. Like I said, one of those is called the Galerkin's method. Another one is called the variational method, which is one of the ones that you see at the very beginning. So let's take a look as to how that looks. Well, before I get on that, any question about this one? I think everybody okay with this exact solution for the beam. What it means is that for every value of x that I give, I find a value of y, and that value of y would can be plotted to find out the deflection, which has to look like this. See? And what we are seeing now is this is like an approximates to a sinusoidal shape. So what we need to do is to come up with the variational method or the Galerkin's method to do this, which we will do next.